This is a slide that had the definition. For a random process, it's a Markov process if this condition is satisfied. That when you're looking at the PDF of the measurement at time n, and likewise the state at time n+1, if you condition this on the entire history, it's equal to what the distribution is when you only condition it on the state at time n.
Actually, now that I think of it, I think that's technically, isn't that a first order Markov? And then second order Markov would be x of n and x of n minus 1.
Yeah, you're right. You're right. So I guess I should have been more careful. First order Markov process is defined this way. But nonetheless, this is what the definition is, and it's what we're using in this class. So again, I'm still not answering the question about memoryless, but...
No, I think this is actually what I was looking for, I think. So that kind of describes everything that you need to know.
Yeah. And we use this simplification in deriving the Bayesian recursions a couple of times, where we had something like this or something like this, and we simplified it to this and to this. And the nice thing is that these two terms we can usually figure out. These PDFs we can figure out directly from the model that we have, the state space model we have. So there's a relatively straightforward path from the state space model to these two probabilities.
I don't want to digress too much, but I guess a simple example comes to mind of an object moving, and so if you know, so with respect to the equation on the bottom, you're saying you only know the previous state will tell you everything you need to know about the next state.
Mm-hmm.
But since velocity would be such a big factor in something moving, would that not be an example of this? Because to know the velocity, you would need multiple previous states.
Usually, in that case, the velocity would be defined as being part of the state.
Oh, okay, I see.
State variable.
Okay, never mind. So I was thinking x is like just a location.
Yeah, that's probably where the mismatch is. X is not just a location.
It's okay.
It's a vector, and it would include all of the relevant dynamics. Good. And this is exactly the kind of questions and discussion I'd like to have more of. It's great. Previous slides that we looked at, this is one of them. The green represents, in this example, our prior distribution, and the posterior is shown by the red. And arguably, you've got more information about where the state is. The standard deviation of the red is not perfectly clear here, but the standard deviation of this red distribution is less, it's smaller than the green. So when you conditioned it on a measurement, you had more information, you had a tighter distribution than you do with the green. And usually it's clearly tighter. I mean, usually it's a substantial improvement when you condition on the measurement as compared to your prior distribution. And we can sort of see that in the other example. Start the recording. Okay. So last time we had a linear process model or state model, where this is an autoregressive process, and I'll talk a lot more about how to build these process models and different ways of modeling the state dynamics later. This is where there's a lot of design that comes in engineering judgment. And then we've got this measurement model that was nonlinear. And Sam asked, I thought, what was a good question, though, we're starting out with this nonlinear thing, but what would happen if this was a simple linear model, if y of n was equal to, in this case, some number times x of n plus noise? And so I added that example to these slides.
With that process model, is that a Markov process if it's linear like that, or does that define a Markov process?
It is a subset of Markov processes.
Okay, subset.
So the Markov property just requires that if we know what x of n is, then there's no benefit. It doesn't change the information or the knowledge we have about the state at time n plus 1 if we've got this state. If you add other information, past observations or past values of what the state is further back in time. So it's really a way of expressing the idea that all the information that you need statistically to estimate x of n plus 1 or to estimate y of n is contained in the state.
So that it could be a function of x of n, and it still would be Markov.
Yes, that's right. That's right.
so a system that's somewhat memoryless.
As you'll soon learn next Wednesday, the key step in this that makes it difficult to implement and computationally inefficient is this integral, evaluating that integral numerically. You're going to find that's the linchpin. And if you were in multi-dimensions, let's say you're even in 2 dimensions, so now you've got a 2-dimensional grid of points over which you have to evaluate a 2-dimensional integral. Now your order of computation, instead of being n squared, is now n to the 4th power. And it gets that much worse in 3 dimensions and so on. Like, it just very rapidly becomes completely impractical, even with the help of Intel in our backyard here, to try to implement that integral numerically. And the key insight, maybe that's too strong a word, the key trick is a better word, that particle filters leverages is a very clever way of implementing that integral that doesn't scale badly with dimension. So it's trying to beat this curse of dimensionality, where right now our computation scales exponentially with the dimension, and we'll see particle filters, really when you boil it all down and say, okay, what's the magic behind particle filters? It's a clever way of implementing that integral, and that's what we'll talk about for the rest of today's lecture. There's less value in studying the measurements and thinking about the PDF of y, because y is what we measure. I mean, we get those numbers. So why would you plot a PDF of y then? You're going to measure that directly. What we really care about is the state, and so that's what we usually focus on. That's what we're trying to estimate. What I had shown you in this example, because kind of an approximation to the prior is sort of shown by the outer reaches. I mean, we basically have a normal distribution that is being multiplied by a likelihood that has bumps that go out to infinity. In the prior knowledge, we rapidly lose information about where the state is, and it can kind of be out like this, and it's kind of growing, and it reaches a steady state. It would be sort of like a Gaussian distribution with roughly a 95% confidence interval that would go from this pink region to that pink region. But based on our measurements, we know that there's some areas where it's very improbable that the state could be there from our measurements. We're able to tighten this up and get a lot better idea than we can from that prior of where the state actually is. And that's the benefit of having those measurements and pulling that information in sort of an optimal way.
And these plots they show the true value. These plots don't actually show the measurement.
These plots do not show the measurement, that's true. And the reason they don't is that this is showing the state. It's not, the measurement could be on a completely different scale. It doesn't make sense to put this in the same scale.
Yeah, it could be that, like there's that 0.2 in the linear example.
Is an example, right?
That wouldn't-
Yeah, and usually the units of your state are just, they're completely different than the units of your measurement. They don't have to be, but they usually are. And we're not thinking about the distribution of y because we could, but there's not much value in doing so. What we're trying to estimate is the state. And y is what we're measuring. We're getting noisy measurements, and so there is a distribution. We don't know exactly what y would be if there was no noise, but there's less value gained in studying the measurements.
Markov process. It only depends on the last state.
That term came up in a couple of lectures ago, and I said, I think so. I mean, it's because I had forgotten what the memoryless property is. Eric, you probably remember. Do you know what the answer is?
I don't know if somewhat memoryless refers to anything. I mean, it's descriptive. I mean, pure memoryless means pure memoryless. Pure memoryless.
That's what I was trying to
It's only on the current observation, not even in the past observations.
So then that would be the same as a Markov property then, if that's the
No,
definition.
because
Oh,
no
that depends on
observations, not, I think pure memoryless doesn't even require previous states. It's only on the current observation. It's memoryless.
Oh, okay. And I remember now why this is ringing some bells. We talked about a memoryless property of dynamic systems. At least I talk about that property in signal processing. That's not what you're talking about. You're talking about a stochastic process.
Yeah.
And I just don't remember, Sam. I can't answer your question because I still don't remember what the memoryless, how that property is defined. Can you tell me? I mean,
So just to make sure that it only depends on the previous state, and that's it. Is that?
yeah, that's right. I think I had the definition of what a Markov process is, actually a little bit earlier in these slides. This was the all right, so here's the example I added. In this case, it's linear. It's actually identical. The process model is identical to what we had in the example with the angle tracker, what was changing over time. In the measurement model, in this case, I just made it linear instead of having that sine term in there. So otherwise, it's the same. And computationally, using I think the trapezoidal rule to do this integral numerically, I think it was probably confusing. In retrospect, one of the things I probably could have explained better is why this integral has to be evaluated. We're evaluating this essentially as a sum, and that requires as many terms in the sum as you have bins that you're integrating over. But there's a question of, well, why do you have to do that twice? And I probably could have made it more clear that for wherever you place your bins, you have to evaluate this integral over all those bins for a given bin of xn, and then you go to the next one. So you end up doing it n of those integrals if you have n bins, and that's why it's an order n squared operation. This will become more clear to you when you do it yourselves, but I realize I probably could have explained that better. In any case, evaluating all those integrals numerically, and holding this, representing this PDF essentially as a histogram, is the way that we're really modeling that PDF, and evaluating this integral. If it's a histogram, you can sort of model that as a sum when you're calculating the integral.
Using the different methods of integration, those are all just sums, though, right?
Essentially, they're just sums. Yeah, whether it's the trapezoidal rule or the rectangular rule or something more elegant, at the end of the day, it's mostly a sum. They're a little bit different in terms of how they handle the edge conditions, but the sums themselves are more or less the same. So this is basically a sum. Yeah, okay, and so there's two answers. If you wave your hands a lot and say, and are willing to sort of ignore some subtleties of the startup, then the answer is yes. But the real answer is no. And the reason that the real answer is no is that the steady state distribution of the state and of the process is different than what it starts off to be, because the initial distribution of the state is up to you. In this case, I'm specifying it to be a Gaussian with a tight uncertainty centered at 0. And in steady state, as we'll see, the variance could be larger or it could be smaller and have a different distribution. So there's this initial startup that technically makes it non-stationary. The other thing that makes it non-stationary is this parameter alpha. If it's 1, you have a random walk process. A random walk process has a variance that grows with time. If you're taking random steps, you have increasing uncertainty about where you are. And if the variance is not constant from one time sample to the next, then it's non-stationary by definition. So, but if alpha is just a smidgen less than 1, if it's not a random walk, then it does approach a stationary process, a stationary distribution. And that's only for this example. These two parameters, your model, can be changing over time. And if it is changing over time, then that again makes it non-stationary. So the techniques we're talking about work just the same and just as well in the non-stationary case. But in this particular example, because alpha is less than 1, if we ignore the startup transient from the initial distribution of x of n, then it's stationary with big quotation marks around it.
So after a certain point in time, it becomes stationary.
It approaches a stationary process. I mean, technically it never actually hits it mathematically, but mostly.
Necessarily grow without bound, right?
That's right. Jeff had asked me, is the process stationary? And what I was thinking about is the distribution of x of n in that case, and whether that distribution is changing over time. The distribution of x of n, the variance of x of n, would also grow if this were a random walk process. But what I just described is a distribution of the marginal distribution of the state and how it changes over time. What I'm showing you plots of is something different. What I'm showing you plots of is the posterior distribution. That's a different distribution than the distribution of this without conditioned on those measurements. In a random walk process, this process is non-stationary, it's unstable, just meaning the variance grows without bound. And the variance, the distribution of this, our prior distribution, does grow with time. However, when we condition it on a measurement, it doesn't. And it doesn't because we're getting something that is closely related to x of n. It's noisy, and so it doesn't give us perfect knowledge about what x of n because of this noise term here, but it does give us knowledge about the state. And so the posterior distribution, the thing that we're trying to track this, even in a random walk process where this is non-stationary, it's unstable, the variance grows without bound, because we're conditioning on a measurement and we're getting something that's related to the state, the width of this distribution doesn't grow without bound. And so in a random walk process actually wouldn't look very much different than what I've shown you.
Kind of like a feedback in a way?
Mm-hmm. Yeah, it's like a feedback. It's there is an analogous idea. We're feeding back some knowledge about the state that's given to us by the measurements we're able to take. Yeah, and that and one way of thinking about that, another idea to bring those two together, is this, the uncertainty, the width of just the probability of x of n grows with time. But when we condition it, when you condition it on y0 to n, what you're doing is, one way of thinking about it is reducing your uncertainty or getting a tighter distribution about the state. In our previous example, I think you can nicely see it in, as I've said a few times, it's important that you be specific about the parameters that you use. And I expect at the end of the term, when you're doing your final reports, most of you will probably have a table of all the parameters, usually the parameters that represent your model design. This is a simple case. And there's two parameters that I added that we didn't have, I wasn't as explicit in the first version of these slides that I've added, but it turns out that they're important. So we've got an autoregressive process, and this is the parameter that controls how much the current state depends on the previous state. We talked about that last time. So I made it 0.99 to give it a good amount of memory so that there's useful information in the state dynamics. This is the standard deviation of the measurement noise. This is the standard deviation of the process noise. So this is, if it were a random walk process, this would be the standard deviation of each step that is taken. So it's a measure of how much variability there is in the state from one step to the next time step. And what I've added are these two terms, which is, I wasn't as clear about this as I should have been, but when you initialize the process, when you start off, you have to start off with an initial guess of where the state is. In some cases, you may know that exactly. In another class I was teaching, I had a student that was working with tracking where a rocket goes from an accelerometer. In time zero, it's starting off on the launch pad, and you have perfect knowledge of where the thing's starting off. So in that case, you know exactly where it is. In other cases, you may say, I've got no knowledge, I've had no measurements, I have no idea where this thing is, and you may have very limited knowledge. And the way that you express that is by expressing a mean for the initial state before you take any measurements at all, and expressing what your standard deviation. In this case, we could do it more generally and say, rather than modeling it as a normal distribution or only thinking about these two parameters, it could be any distribution you want. But I'm assuming in this example that it's Gaussian, and it's got a mean of 0 for the initial state, and that our uncertainty about the state is not bad, that we have actually a pretty good idea of where the state is starting off. So a standard deviation of 0.2. I could have made that big if I had a lot of uncertainty about where we were starting off. So it's another parameter that we should think about.
Are all those parameters state variables, or they, some of them are not? in the state?
Some are
vector?
not. So this is, in this case, the state is just a scalar. As we move ahead, these will become matrices and vectors because we're talking about a vector. But for now, we're talking about a scalar. And so these two parameters are of the same dimension as your state vector and are about the state. It's about what do you know about the state at time zero before you take any measurements. That's what these two represent. This is the process noise, and it's usually the same dimension as the state vector. So in this case, this is would be in the same units as the units of the state. So if you're measuring velocity in meters per second, then, and that was your state, then this would be in meters per second also.
So the first two are components of the vector, of the state vector, that you could use them as components.
Right. So it can get a little tricky. There can be a matrix involved that multiplies times the noise you have, and then things get a little bit weird, but generally speaking, what I said is true, and it's better to do it this way, more directly. For the duration of this class, that'll be true. This will have the same units as the state vector. The measurement noise is different. Your measurement may be in completely different units than that of your state vector. You may be estimating position in units of meters, but you may be representing the state in units of meters per second. So this is in the same units as whatever your vector of measurements is. In this case, we're doing a scalar case, so the measurements are scalar. And this is multiplies by the state, so this is unitless because it essentially transforms whatever the units are of the state vector into another state vector. And so it's a unitless scalar.
Do these processes need to be stationary?
Oh, that's a good question. That's a really good question. And yeah, as a company, don't be too concerned. It's not critical.
Measurement.
For the ideas that we're talking about. So this is just a plot of the state and of y-ven, and you should see, in this case, there should be a visual correspondence between the two, because y-ven is just a scaled version of x-ven. So you can see here that it goes up, and y-ven goes up, this goes up, this goes up, goes down, this goes down. There's a linear correlation between the two, just as you would expect. You'd still be hard-pressed to, I think, to say, based on this sequence of y of n, what do you think the state is if you're just trying to eyeball it, even knowing what the relationship is?
Measurement.
All right, and then maybe the second most important slide, here's what it looks like. This is the posterior distribution, that thing we care about so much, the marginal posterior distribution and how it changes over time. And just as I had said on Monday, it's Gaussian. And I didn't make it be Gaussian, but I knew theoretically it had to be Gaussian, and sure enough, when you do the integration and run the algorithm, even though it could represent a non-Gaussian distribution, it ends up being Gaussian, just as you would expect. And the other thing that was interesting about this that make is when you zoom in on what's happening initially, as I said, we start off with our knowledge of the state. We start off assuming before we have any measurements the mean is zero, and so the estimate is at zero as you would expect, regardless of whether you're doing mean, median, mode, it doesn't matter. It all lands at the same point. And if you look at how much uncertainty there is, it's controlled by that same distribution that we specified. We knew how much uncertainty there was. That was one of the things we had to specify. How much knowledge do you have about the state initially? And it's pretty tight. As we get more measurements, though, the state can change in a way that we know something about, but there's uncertainty in that because it's following this autoregressive process. And as we take measurements, we're taking noisy measurements. So if you look at the width of this distribution, you'll see in this particular example that it gets wider as time goes on. Now, maybe what I should have done, but didn't do, is do another example where I say, I've got no idea what the initial state is, and give it a very large standard deviation. So in that case, this would be very wide, and what you would see over time is it would actually narrow down. So whether it narrows down or broadens out really is mostly a function of just how you express your uncertainty about what the initial state is. The other thing that you might take from this is a question about stationarity, and technically it's not stationary in this case, and you can see it here that the width of the distribution is narrower and it gets wider. And it'll do that
the
consistently.
variance of the distribution is growing.
So the variance is changing over time, and if we had initialized this to be large, it would shrink down over time. If we had initialized it to be the same, if did the math, figured out what the steady state variance is, then in that case it would have been a stationary process. So, and you can see after, not many time steps, after just even 10 time steps, the width of this is not changing over time. It may change a little bit just due to estimation error, but it reaches steady state in like 10 steps, more or less.
So if alpha was 1, would that width eventually just continuously grow and then it would be dark blue for the whole image at some point?
Yeah, that's a good question. And it's only dark blue because of the projector. It's actually gray. But can anyone else answer that question?
Should grow. That's what you're saying earlier, right? The variance is gonna grow in a random walk problem.
Okay. Any other thoughts? Jimmy, I really appreciate that question because it makes it clear that there's a distinction that generally speaking, when you represent a linear state space process that could be time varying, at least in this class, we'll represent it in this form. So rather than having a nonlinear function here of the state and of the noise, the process noise, and rather than having a nonlinear function here of the state and the measurement noise, instead what we have is additive noise, and we've got a linear function of the state. Now this is a matrix, and so it's not just scaling the state vector. It could do the equivalent of rotating it as well as scaling it is part of this process. And likewise, the measurements, this is a transformation, a linear transformation of the state vector. So you have to think this is more than the equivalent of just scaling the state. You're transforming the state into your set of measurements. But this is the general form for a linear, stochastic, time-varying, non-stationary state space model. And what we saw when we went through this, the example with our scalar example of this, is that the posterior distribution ended up being Gaussian. And you can prove that that's the case. It shouldn't be too surprising because if the state is initially Gaussian, if you're adding Gaussian noise, and y of n now is just a linear combination of a random variable that's Gaussian, and you're adding Gaussian noise to it, then a sum of Gaussians or an arbitrary linear combination of Gaussians will also give you a Gaussian distribution. So everything just ends up being Gaussian in that case. And if it's Gaussian, the nice thing about being Gaussian is a Gaussian distribution is completely characterized by just knowing the mean and the covariance. If you've got those two, then you've completely characterized that PDF. And what we'll see later in the course is that the Kalman filter, what it gives you is the same thing that we just saw. It gives you the posterior distribution, but it directly tracks the posterior mean and the posterior covariance. And with those, you can then do the same thing that we just did. But it is directly tracking those two parameters that characterize a Gaussian distribution. And that's cool, but it's also limited because if your noise isn't Gaussian, if your process is nonlinear, there's so many things that could, just a small change, make that representation, where you're representing the posterior really as the mean and the covariance, render that inappropriate or useless or a very rough approximation of what you're actually interested in. That being said, this does have, is it 40 years now? It's got 40 years of use, wide use by engineers, and so we've gotten a lot of mileage out of the Kalman filter recursions and some of the approximations that enable us to apply those recursions, even in the nonlinear case. But it's worth keeping in mind that when we move to these techniques, we're really representing the posterior with just these set of parameters. And if our distribution is multimodal, then we're not capturing those features by representing it with just those parameters. And we don't have that limitation with particle filters. So that's one of the advantages that we'll see as we move to particle filters. So, do you guys have any more questions on this topic or this set of slides before we move on to the key idea for particle filters? No? Okay. Well, let me just make one final point as long as I've got these slides open. And that is